Hello again, everyone. Our next lesson is going to be on the intersection of lines and planes. Okay, and again, to help visualize what's going on here, I'm going to do a little story with a dog again. And actually, this takes me back to when my family had a dog when I was younger. One day we got the brilliant idea of getting out a flashlight and pointing at the floor and letting him chase it around the floor, which was funny at first. But then I decided to use the flashlight to lead him up to the ceiling, okay, and have a look at the ceiling. So something like this. Okay, there we go. But then he became absolutely transfixed on the ceiling. Okay, and for the next 4 days, he just barked and barked and barked and barked, and we couldn't hear the end of it. Okay. And my parents didn't really like me for a while after that, but those things happen sometimes. Okay, so what we're really looking for here is that when I shine the flashlight, right, it'll hit some point on the ceiling, okay, and I'd like to know where that point is. So if I know the path of the line, I know the equation of the plane, I should be able to figure out where that point is, okay? And just like we had cases for intersections of lines, okay, we also have cases for this. So, right, most of the time when I shine light on the ceiling, here's if I tilt it a little bit here, it's still going to hit one point on the ceiling. Okay, and if this went on further, right, I know it's not showing that here, but this would keep going and it would hit the ceiling somewhere over here, right? So most of the time it's just on the ceiling. Okay. The only way it's not going to hit the ceiling is if a beam of light is parallel. Okay, something like this. It's never going to intersect the ceiling. Okay, so I have no solution then. And the final case would be if I can kind of insert or hold the flashlight right against the ceiling. Okay, then the beam of light is right on the ceiling. And then I would have an infinite number of solutions, right? Every single point on this beam of light, okay, is a point that's also on the plane if it's kind of right against the surface there. So that's the first part. Those are our three cases for the intersection between the line and the plane. Okay, either I can have one solution when the line is at an angle to the plane. Okay, I can have an infinite number of solutions. That's when the line is sitting in the plane. So every single point on the line is a solution. Okay, and finally, I could have no solutions. Okay, and that's when the line would be parallel to the plane, okay, above it. Okay, and you know, it's hard to draw here, but you know, it could be parallel kind of going in this direction, okay, away from me into the computer screen. But again, it's kind of hard to demonstrate here in the video. Okay, so those are the cases. And our first example, we're going to go through the solutions, so how to solve for this, and what it kind of looks like as you run it through. So for example one, we're going to determine the intersection, if any, of the following lines with this plane, 3x minus 2y minus z is equal to 6. Okay, and one little thing to note here, it's much easier to work with the scalar form of the plane. So if for some reason you had the vector form of the plane, you'd want to put it in scalar form first before you start trying to work through the solution. You can do it from the vector form, but it's a lot messier. Okay. So the way we're going to do this, like what we did with the intersections of lines, is we're going to first write out our line again in the parametric form. Okay, so for my x-coordinate, that would be 1 plus t, y equals 1 plus 4t, and z is equal to 2 minus 2t. Okay. Now, I'm just going to take the equation of the plane, okay, and I'm going to substitute in my parameters x, y, and z, where I see x, y, and z in the equation. And that's pretty much the whole thing. Okay. So I have 3 times x, and x is equal to 1 plus t. And then subtract 2 times y, which is 1 plus 4t. minus z, which is 2 minus 2t, and then equals 6. Okay, this equation only has one variable in it now. It's got t, so we just have to run it through and solve it for t. So we'll just start running through the algebra here. So I've got 3 plus 3t minus 2 minus 8t minus 2 plus 2t is equal to 6. So I've got 3, take away 8 plus 2. That would be negative 3t. And then I've got 3, take away 2, so minus 1 is equal to 6. So I bring the 1 over, negative 3t is equal to 7. And so t is negative 7/3. Now that I have my value for t, I'm going to go back to my parametric form of the equation and use that to figure out x, y, and z. Okay, so now I have x is equal to 1 plus t, which is negative 7/3. And that is equal to negative 4/3. Okay, y is equal to 1 plus 4 times negative 7/3. Let's see, that would be negative 20/3 plus 3/3, so negative 25/3. And z was equal to, that was a 2, I believe. So 2 minus 2 times negative 7/3. And that would be, let's see, 6 plus 14, so 20/3. Okay, so therefore, my point of intersection is going to be negative 4/3, negative 25/3, and 20/3. A way I could verify to see if this is actually the case would be to take my point and plug it back into that equation of the plane and make sure it's actually a point on the plane as well. Okay, I know it's messy because the fractions, but let's take a moment and just see if that actually works. So as a quick check, okay, I'm going to plug that point in. So it was 3 times negative 4/3 minus 2, double checking here, yep, times negative 25/3 minus 20/3, and that's supposed to be equal to 6. So I'm really hoping this works out. First term is minus 4. Then I'm going to have plus 50/3 minus 20/3. And actually, I should probably just put that back as a fraction because it's all in thirds anyway. So negative 12/3. That's supposed to equal 6. So I've got 50. Let's see, 50 take away 20 is 30, take away 12 is 18. So I have 18/3 equals 6, and 6 equals 6, and we're good. Okay, so that's all you really have to do. Take the parametric form, plug it in, and run with it, and you get your point of intersection. So let's try another one. Here's the same plane, and here's a new line. Okay, so we'll start the same process here. We'll write out the parametric form. So x equals 3 minus 2t. Y equals 4 plus 7t. And z is equal to negative 5 minus 20t. Okay, we take our equation and plug in our parameters. So 3 times 3 minus 2t plus, minus 2 plus plus 7t minus negative 5 minus 20t is supposed to be equal to 6. Okay, so going across here, I have 9 minus 6t minus 8 minus 14t, and then I've got plus 5 plus 20t is equal to 6. Okay, so starting with my t terms, I've got take away 6, take away 14, that's negative 20, then plus 20. So I have 0t at the moment. Okay, on the other side, I have 9, take away 8, which is 1, plus 5 is 6, so plus 6 is equal to 6. Okay, if I subtract 6 from both sides, I'm going to have 0t is equal to 0. Of course, 0 times t is really just 0, so I have 0 equals 0. Okay, what this means is I got something that's always true. Okay, so this line actually lies in the plane. Okay, so this line lies in the plane. Okay, that means at any point I can generate on this line should work in the plane. So right, again, a quick verification, if I plugged in 3, this point, 3, 4, negative 5, right, I would have, what, 9, take away 8, and then plus 5 gives you 6, and it works. Okay, if you generate another point, it will also work. Okay, so that's the sign, right? I got the 0 equals 0, which is always true, which means it didn't matter what value of t I got, it would work. And that means that the entire line is in the plane. Okay, next one. So here's another line, and we'll run through that process one more time. So parametric form. Okay, line 3 is x equals 8 plus t, y equals negative 3 plus t, and z is equal to 1 plus t. Okay, I run that into the equation. So 3, 8 plus t, minus 2, negative 3 plus t, minus 1 plus t is equal to 6. So 24 plus 3t plus 6 minus 2t minus 1 minus t is equal to 6. Okay, so we're going to start with t. I've got 3t minus 2 is 1t minus t. Oh, there's 0t again. And for my constants, I have 24 plus 6 is 30, minus 1 is 29. Okay, so plus 29 equals 6. If I bring that over, I would have 0t equals negative 23. 0 equals negative 23. Okay. I'm hoping you knew that. 0 is also negative 23. No, of course not. This doesn't make any sense. Okay, so that means that there is no solution, and therefore this line is parallel to the plane. Okay, so this line is parallel to the plane. Okay, so yeah, that's how that turns out. If they're parallel, they don't intersect at all. When you start solving for t, you'll get something like this that says they're not parallel. Okay, sorry, the fact that you get nonsense, 0 equals negative 23 means they're going to be parallel. All right, our final thing, now that we know this is parallel, okay, we're going to talk about distance. Okay, determine the distance between the line and the plane in the example we just did. Okay, so now I know they don't cross at all, but I might be curious to know how far apart the two things are. Okay, And this process is actually a little bit easier than yesterday's stuff, although it's related to it. So again, we'll draw a picture out here. Okay, if there's my plane, okay, and I have my line, which is above it. Okay, I know some point on the line. We'll call that A. Okay, I know the plane has a normal. Okay, right? That's given in my equation. So there's some kind of a vector that goes straight up and down from the plane. Now I would really like to know what that distance is. Where does it hit with A there? Okay, so kind of like what we did in our last example in the last note. Okay, I'll find some point on the plane, right, X, create a vector running between them, and then simply project that onto the normal because I already know what my perpendicular direction is. Okay, and we're pretty much all set to go here. Okay, so I have my point on the line. That would be this right here. We'll call that our A. Okay, now I need a point on the plane, so I'm going to have to generate something that's on the plane. So I can just pick values for X and Y and figure out what the Z would be. Okay, we did get a point that was on the plane way back in example 1A, but that was with the messy fractions, so let's not use that one. So let's say I let X equal 1 and Y equal -1. Okay, then I would have 3 times 1 minus 2 times -1 minus Z is equal to 6. So I've got 3 plus 2 minus Z is equal to 6. So that means that negative Z is equal to 1. So Z equals -1. Okay, so my point X is going to be 1, -1, and -1. Okay, again, it shouldn't matter what point it is. This process should still give us the same answer. Okay, so I'm going to create now my vector A to X. Okay, so AX equals, let's see, 1 minus H is -7, -1 minus -3 is +2, and -1 minus 1 is -2. All right, now I'm going to project this onto my normal vector. Okay, and just so I have it written down here, my normal vector, right, is those coefficients from the plane. So I have 3, -2, -1. Okay, again, we're still going to use that same little shortcut we had from the last lesson. So I want the magnitude of the projection of AX onto the normal. Okay, and that's going to be the magnitude of the dot product between those two things, okay, over the magnitude of the normal vector. Okay, so we'll start with the magnitude of the normal vector. That's going to be 9 plus 4 plus 1, so that's going to be square root of 14 on the bottom. Okay, and the dot product, let's see, I've got -7 times 3, so -21 plus 2 times 6 is -4, so -4, -2 times 1 plus 2. Okay, so that gives me, oh, I need magnitude here as well. So it's -23, so 23 over the square root of 14. And let's get an actual number for that. Although I shouldn't say that. I mean, this is a number, 23 over root 14. But the decimal equivalent of that is about 6.15. Okay, so that is the distance from the line to the plane. That's how far apart they would be. Okay, final side note before I wrap up with the practice work here is I was going back and forth with my online note to make sure my numbers were working out the way I expected. And in example 2 here, right, I used a different point, 2, 0, 0, and I got a slightly different answer. and I was honestly freaking out about this for a little bit. Like I couldn't figure out what the problem was. And then I realized I had a typo, right? This right here, this one should be a -1, and it would also come out to 23 over 14. Okay, so there you go. Um, that's what the answer is supposed to be. So there's a practice work starting on page 479. Okay, those questions, and it's all about finding the distance between lines and planes and intersection between the line and the plane. Okay, uh, thanks for watching. Oh, and one last thing before I forget, if you're looking at the calendar, okay, you might know that I left Friday's date blank here. Okay, I'm going to leave that there. Okay, so I'm not going to do a new lesson tomorrow. We'll start the new lessons next week. However, I will still post a homework take-up video. So yeah, send me your homework questions, and I will answer those and post those here. Okay, again, thanks, and we'll see you next time.